Hello, so today we are doing this problem called course schedule. It's a medium problem, and the problem says we have a total of n courses, and they are labeled from 0 to n-1, and some courses have prerequisite. So for example, to take course 0, you have to take first course 1, which is expressed with this pair. So the first element means basically the last element is what it is required to take the first element. It's a little bit reversed than what we usually used to with graphs, which is the first element, the second element depends on the first element. Here it's the first element depends on the second element. And given the total number of these courses and these list of prerequisite pairs, the question is it possible to finish all courses, essentially? So we have here this input, for example, 1 and 0, and so let's just draw it up here. So we have these two courses, and 0. So basically, this means that to take course 1, we have to have taken 0 first. And this is entirely possible. We just take course 0, finish it up, and then take course 1, right? For the second example, though, which is this one, so to take course 0, we have to take course 1. That's what this one says. Yes. And then to take course 1, we have to take course 0. So there is also this relationship that is going out here. So how can we take course 1, we have to take course 0, and to take course 0, we have to take course 1. So we can see the arrows here, we have a cycle. And so essentially what this problem boils down to is finding if a topological sorter, topological ordering is possible. And topological ordering is just a fancy term for can we like traverse this graph here and finish each node one after the other, like finish course 1, then go do course 2, then go do course 3, extra, without having, like, for example, taking course 2 and having to go back and take course 0 again, which doesn't make sense. So basically it's equivalent to checking that there is no cycle. So that's the problem, and so we have the input, and we might assume that there are no duplicate edges. And so let's think about this problem here. So the first thing that comes to mind is to use DFS. This is a graph problem, and DFS can easily determine there is no cycle. And the way we do that is just we traverse the nodes with DFS. So traverse the nodes with DFS. And so traverse the nodes with DFS, and we need to keep plus keep two auxiliary data structures, so 2 DS auxiliary data structures that we need to keep track of some information. One of them is the visited set, the other one is the visiting set. And basically what this one means is we are done exploring, and a neighbor contains nodes that we are done exploring, and which means including their neighbors. Basically that's what DFS does. It goes all the way down until reaching all the neighbors, right? And visiting list means we started exploring this node but haven't finished it going through all its neighbors yet, which is exactly what DFS does. So let's say we had this graph that is 0 to 1 and then goes all the way to some n value or some x value. And so for this node 0, it's not done until we visited x. And so the visiting set here, for example, at this point here, our visiting set would contain 0, 1, because still 1 also until we get to x, because it's connected to it, we haven't done we haven't finished it yet. But once we reach X, and here also at this point our visited set will still be containing nothing. But if once we reach X, which means that's the end of all the so now the first thing we do is, okay, X doesn't have any neighbors, so we visited X. And now since we are done, we keep backtracking with our recursive function. We keep popping up the recursive function in the stack. And then we say, okay, we get to 1. At the 1, all its neighbors have been visited. We remove it from the visiting set. And then we add it to this one. And we would have added also all the intermediary neighbors here. And then we pop again the recursive function stack, the stack of functions basically. We pop another level, and now we get to 0. We remove it from the visiting set and we add it here. So what are the steps that we did here? Once all nodes of all neighbors of a node have been visited, remove it from visiting set because we are done, and add it to visited. And also when we start exploring a node, that's what we did every time we get to a node and we start exploring its neighbors, we add it to the visiting set. So when we start exploring a node, add it to the visiting list. And so that's essentially the DFS that we are going to follow. So it's normal DFS that you are used to, except with this extra visiting set that is going to help us to know if there is a cycle, which means that we have a problem with our topological order and we can't do it. And so if we call DFS on a node that is already in the visiting set, that means we have a cycle. Because let's say I'm here, right? And I have all of these in visiting set, and then my node here, let's say node Y, is somehow linked to 1, has an edge to 1. So that means that when I call the neighbors DFS on the neighbors of Y, I will go back to 1, and 1 is at that moment 1 is my visiting set, which means I'm still in the process of exploring 1 or exploring its neighbors, and then I'm going back to it. So that means we have that cycle. Like here we will see it very quickly. We'll get to 1, and 1 its neighbors is 0, so we'll call DFS on 0, but 0 is currently in our visiting set because we haven't finished visiting 1, and so we'll notice that it's a cycle. And so when we notice that it's a cycle, that means that topological ordering is not possible. So just return false. Otherwise, there is no cycle here, and keep exploring. Oh no, there is one thing to keep in mind though, is that we may have, let's say, a node x1 or x that is to y, that is to something else z, but then we may have something u here that is going to v, and this may be this is maybe the same graph. Like this is a valid graph, but it just has 2 connected components. So starting from here and visiting everything with DFS, that's not enough. We have to also go to the other nodes that have not been visited. We may also have some W here that is going to M, for example, or something like that. So it may be a lot of disconnected components. And so traverse nodes with DFS. So this traverse all nodes with DFS here. All nodes with DFS. And so we will need to have an outer loop to make sure we touch all nodes in the graph. But if at the end, now one other things we need to do is no, actually that's all we need to do. There is nothing else we need to do. And so this is pretty much it. We go through all nodes in the graph. Each one of them we see if it's not visited yet, we start the DFS on it. and we keep track of these two lists so that we can determine if there is a cycle. As soon as we find a cycle in one of the nodes, starting from one of the nodes, we return false, that it's not possible to have a topological ordering. And the way we will find the cycle is by using this visiting set. If we come back to a node that we already went to, which is currently in our visiting set, that means we have a cycle, so we return that we have a cycle, and we can't finish, basically. We can't do all courses because there is no way there is that cycle that preventing us from taking any course before another. And so let's code this up quickly. So basically, first though, let me just talk about the time complexity of this. So this is just normal DFS, and we are going through the entire graph, so it's pretty much of E plus B. And its space complexity is, we have those two lists, which are both, at most they will contain the number of vertices or the number of nodes. They can't be like more than that, so it's OV. But here you can notice that we are using two sets, visiting and visited. There is a trick to avoid like at least having this space complexity 2 times, which is we can just have one list called visit and then have multiple values. So if it's 1, just instead of checking if in list, we check just the value. So 0 means not touched yet, so it's not in the list. So not in the list, equivalent to not in the list in the case above, in this method. And we can have -1b that we are visiting it. We are currently visiting it. So if the value is -1, that's equivalent to the fact that it's in the visiting list, and 1 would be equivalent to being in the visited set. And so having this avoids having these two lists. So that's a nice trick to keep in mind whenever you need to use multiple lists with DFS or BFS. You can just make an array of the size of all the nodes, if we know that in advance, and just put different values where each one represents a different state. And so yeah, that's pretty much it. Let's start coding this. And so first we have our graph that we are going to initialize, and our graph is just it's just going to be basically, we can make it an array, we can make it a map, whichever one is easier for you, but I'm just going to make it a list, an empty list. Starts out as an empty list for the range. We know the nodes in advance, the number of nodes in advance, and then we are going to have the visit list that we talked about here, and that would be 0 for in the range also of NIM courses. So, and the value 0 essentially represent nothing, not touched yet, so that's what we put there. And we are going to go through the prerequisite that we have here. And so that, just to do something here to make it easier, since we said it's a little bit reversed the meaning here for the edge, and so we are going to make that happen with this GI, and in prerequisites, this list that we have here. And so in our graph of I is going to be equal, we are going to add J. And after that, are going to start our DFS on I. And also another thing we need to do is, so we need to go through, traverse all the nodes with DFS, right? That's what we said. So for, we are going to traverse all the nodes, so we know that the nodes are range of NIM courses. And so we are going to check if it's not visited yet, then we are going to start visiting it. And so we can say, either we can say visit I is different than mine, is equal to 0, then we go explore, or we can just let our DFS method handle that. I'll show you later. So we can just, if our DFS says nope, we have a cycle, so this DFS checks for a cycle, that means we can't finish because there is a cycle, so we return false. If we went through all nodes and we didn't find a cycle, we return true. Now our DFS is going to do the check that I wanted to do first here. So what is that check? So if visit of I is equal to 1, which means we have already visited, then we can just return true, because return false, there is no cycle. It's already visited and we didn't find a cycle. Sorry, actually, so checks for a cycle here. If there is a cycle, returns false. So essentially, you can think this checks that graph is acyclic. If there is a cycle, returns false, else return true. That's what the specification of this DFS. And so we are going to say if not DFS, that means it's not acyclic, which means there is a cycle. And in that case, we return false. And so here equal to 1, that means there is not a cycle. We already visited it, so we just want to skip it. So here it's acyclic, so we need to return true. Now if it's in visiting state, equal to -1, which means here we said if we call DFS on node that is already in the visiting list, that means we have a cycle. And so that means we have a cycle, so we need to return false. So return false. And we said also when we explore a node, we explore all its neighbors, and we also add it to the visiting set. That's what we said here. When we start exploring 0, we add it to the visiting set and we start exploring all its neighbors. And so we give it a visiting state, and we said we go through the neighbors. And so our neighbors, the neighbors, we get them with graph, so graph of I, and we need to do DFS and check also there is not a cycle starting from that neighbor. So if not DFS, which means there is a cycle, it's not acyclic, which is J here. So if there is a cycle starting from that node, we need to return false. And at the end, that means we explored all the neighbors of I. Then we need to add it to the visited set, which means we need to set its state to 1. And so how we do that? We do it by doing visit of I is equal to 1. And then we return true, because we didn't find any neighbor that had a cycle, so we return true. And that's pretty much it. That should be it. So we are just doing DFS, and we are going through all the nodes, and we are checking if there is a cycle, or there is a cycle in one of the neighbors, and we mark as visiting when we start exploring it, and we mark as visited when we are done exploring it. And so let's run this. I have a syntax error here. Okay, because we didn't have this. Okay, now let's try with the other test case. Okay, so let's submit this. Okay, looks like it passes. Good. So yeah, so this DFS solution passes, and often when we have a graph problem that can be solved with DFS, we can think if there is a way to solve it with BFS. And for this problem, there is. So let's see how we can do that. Okay, let me just copy this so that I don't. Okay. Now, how can we solve the BFS solution? You solve it using BFS. So with BFS, the solution is slightly different, but it's still the same idea. It's still a similar idea. So basically, with DFS, what we are going to do is use something called in degree, or you can in degree basically, which means how many edges are coming into this node, right? And here in our problem, let's say we have node 1, or let's say we have node X. If it has, let's say, all these edges coming to it, like this, then these, let's say these edges are pointing to X. That means that, maybe let me just Google a graph example so that it can be easier to see. Yep, so for example here in this in this image here, you can see that N4, for example, has 2 edges coming into it, right? So that means it has in degree of 2. N5 here has 1 edge coming into it. That means it has in degree of 1. So that's the explanation of in degree. Here, for example, X here has in degree of 2. So you can see in our course problem, if a graph has 0 in degree, let's say we have Y here that doesn't have anything connected to it, but let's say it has an edge to X, this Y has in degree 0. So in degree of X is 2 and in degree of Y is 0. So when something has in degree of 0, that means we can it's a course, we can take that course right away, right? And so we are going to represent this taking the course right away with just adding it to the BFS queue, right? And so what we are going to do is go through the steps we are going to do is first go through all basically calculate the in degree of all nodes in the graph. Then our second step would be to go through all in degrees and add those with 0 in degree to BFS queue. Because essentially what does this mean if it has in degree 0? Those we can take right away. So let's just put them in the queue, take those courses, and as a consequence we can, so as a consequence if we take a course, we can take all those that depend on it. All those that depend on it have 1 less dependency, right? And we are going to represent that by subtracting 1 from the count of its in degrees. So in this graph here, if we take, let's say, course N5, yeah, N5 maybe is not the best example. Let me maybe course topological sort graph. Okay, so let's see here if there is a one with in degree 0. There is a cycle with this one. No, there isn't a cycle with this one. Let's see if there is one that is easier. Yeah. Okay, so this is easier. So if we look at these courses here, course CS170 doesn't have any in degrees. There is no incoming edges to it, which means it doesn't depend on any course, so we can take it right away. And so when we take it, then course CS270 now has 1 less dependency, has 1 less node coming into it, and so we can subtract its in degree by 1. And its in degree, which was the number of edges coming into it, was just 1, because that's just this one. That's just CS170, and so now it has in degree 0. So now we can take it as a course, and so now that means that go through in degree and those, then start BFS, and all and pop from the queue, And that's what we would have done here by popping CS 170. And then go through all neighbors of the popped neighbors of. So let's call that X, what we popped. All neighbors of X, and subtract their in degree by 1. Because that means there is one less dependency they depend on. And then if any of these neighbors became with in degree 0, which is what happened in this case CS 217. Now it had in degree 1 before we processed CS 170, but now it has in degree 0, and so we need to add it to the queue. And for example here, when we add it to the queue, next pass we will pop this CS 270, and then we will say, look at all its neighbors, so CS 381 and CS 361, and each, for example, this one had in degree just, CS 381 has in degree just 1 before popping this 270, and so we subtract by 1, and now it has 0, and so we add it to the queue and we process it next time. And then once we do all of this and the queue becomes empty, which is the end of our BFS, we need to check one thing. So here we need to count as we are going along. We need to keep counting the nodes we added to the queue, because those are the nodes we added to the queue. Those are the courses we've taken. So why are we doing this? I will tell you in a second, because the last step we are going to do is, let's call this count. If count is equal to the number of courses, that means we were able to process all courses. But if not, that means there were some courses that we couldn't, that their in degree didn't reach 0, basically. And at that point, if their in degree didn't reach 0, that means there was still some dependency. So either there was a cycle, or there was probably a cycle, because we couldn't reach in degree 0, so we couldn't take them. And so that means we can't finish. And so these are the steps for BFS, and pretty much we are just using this concept of in degree to make it easier for us. And when an in degree becomes 0, we can take that course, and so we add it to the queue. Now, what is the time complexity for this? That's just OV plus E. And what is the space complexity? So we have this array for in degrees that we will have, and then we will have the graph also that we are going to construct, just something to help us with processing the neighbors. And so the graph would be space OV, probably actually OV plus E, because it's going to be, for each vertex we'll have a list, and each list would be E. And then the other one is also for the in degree, which would be OV, which because it's for each vertex, and so overall the space complexity is just OV plus E. And yeah, so that's pretty much it for this. So let's just start coding our BFS, and can finish. And just take the signature of the function here. Okay, so let's start coding it up. So first we need our graph in the same way that we did before. We could use a map. I'm just using a list, same thing. So in range of number of courses, just too hard to type number of courses, so I'm just going to call it n. And this one also, I'm just going to make it smaller. And so we have that as a graph, and then we need the in degree. And so they all start out with in degree 0 until we check in the graph what do they have really. And so this is for a range of n, which is the number of courses, And then now we go through the graph so that we can calculate the in degree of this. And so we go through and calculate the graph by going through the prerequisite. And this just represents what I said earlier, that the representation is a little bit flipped. The direction is actually the course that we depend on, that we need to take first, is the last one, and the one that needs that one is the one on the first position. And so that's just represented by this flip for I and j. And then we need to add to the graph and say we need this for and then for the in degree. So what does this mean is there is an edge from I to j. So that means that there is an incoming edge to j, and so the in degree of j is increased by 1. So the direction here basically is that we go from node I to node j. So there is one more incoming edge to j, but no, that's not the case here. And so after that we will start our queue for BFS, and so our queue is going to be a DQ, of course, that we are going to initialize with what? With all those that have in degree 0. That's what we said. Go through in degrees and add those with 0 in degree to BFS queue. I'm just going to use this list comprehension to do that, and so I'm just going to go through I for I in range. So all the courses that have in degree of 0. And then I'm going to start my BFS, and I'm going to pop left so that we can get the first element, and that's what we are going to call course. And then we are going to go through, or actually let's just call it I to make this simpler. And then we are going to go through its neighbors, so graph of I, which is this step here, go through all of its neighbors. So this is 4. And start BFS and pop from the queue. That's step 3 here, and this is step 2. And calculate the in degrees. This is step 1, the in degrees and graph, or and adjacency list. And then now we need to decrement 1 from each in degree. So its in degree of g becomes 1 minus 1. And after that, and subtract minus 1. If any of these neighbors became within degree 0, then we need to add it to the queue. So that means we need to check that in degree of this became, if it became 0, then we need to add it to the queue, because that means we can process it now. We can take that course, and so we need to add j. And then keep counting this. We said keep counting the nodes we add to the queue. So that means here we are going to initialize by the length of the queue. Those are the nodes that we added to the queue. And then every time we add something to the queue, we are just going to increase it by 1. And then at the end, if count is equal to the number of courses, that means we are able to process all courses. So we are going to return if count is equal to the number of courses, which is m. And that's pretty much all there is to it. So let's run this and see if it works. Yeah, so this should be indented like this. Okay, so here I call it j instead of a graph. Oh, my in degree should be 0. Actually, it's not a list, it's one number. Okay, so that's good. Let's try the other test case, which was just 1 0. So, and there are 2. Yeah. Okay, let's submit. Okay, so that passes. And the insight from this problem is one, that topological, to find, to test if there is topological ordering, we just need to check that there is no cycle, because if there is a cycle, that means we can't have a topological ordering. We can't have, or sometimes it's called also topological sorting. The other insight is we can find that out using both DFS and BFS. Another insight, I think, is this concept of in degree, and using that to both find the topological sorting, but maybe it can help out with other problems. That an in degree of 0 means there is no dependency, there is no incoming edges, and so I don't know, that may help in some problems. Yeah, that's it for now. See you next time. Bye.